Two spacecraft launched in 1977 just crossed the edge of our solar system, and what they found out there destroyed every scientific model we had. The boundary was billions of miles in the wrong place. The shape was completely wrong, and interstellar space had properties nobody predicted. Today we uncover 7 shocking discoveries that rewrote everything we thought we knew about where our solar system ends and what lies beyond. Before we start, if you enjoy exploring the universe with us, a quiet subscribe helps this channel reach further. Now let's begin. In 2012, a signal weaker than a nightlight bulb crossed 17 billion kilometers of empty space and arrived at Earth. It took 22 hours to make that journey. And when scientists finally decoded what it was saying, everything they believed about the edge of our solar system collapsed in a single moment. That signal came from Voyager 1. A spacecraft the size of a small car built with technology from the early 1970s, running on computers with less processing power than a modern kitchen appliance. It had been traveling for 35 years, and it had just discovered that every model, every calculation, every confident prediction scientists had made about where the solar system ends was wrong. Not slightly wrong, billions of miles wrong. This is that story. In the summer of 1977, NASA prepared to launch 2 spacecraft that would become the most traveled objects in human history. Voyager 2 lifted off on August 20th. Voyager 1 followed on September 5th, taking a faster trajectory. The names reflect their arrival order at the planets, not their launch sequence, a small but telling detail about how carefully every aspect of this mission was planned. Each spacecraft weighed 825 kilograms. Each stood roughly 3.7 meters tall, and each carried a suite of scientific instruments designed to study Jupiter and Saturn, 2 planets, a 5-year mission, then silence as the power faded and the spacecraft drifted into the outer darkness. That was the plan. Nobody talked seriously about what might happen after year 5. Nobody drew up contingency documents for year 47. Nobody needed to because the spacecraft were never supposed to last that long. The computers aboard each Voyager operate on 68 kilobytes of total memory. 68 kilobytes. A single low-resolution photograph on your phone takes up more space than that. The rice cooker, sitting on your kitchen counter, the one with the digital timer and the warming function, almost certainly runs more sophisticated software than the machines guiding these spacecraft across interstellar space. And yet those machines are still receiving commands, still executing instructions, still returning data from a distance so vast that the signal takes more than 22 hours just to reach us. The world that built Voyager looks almost unrecognizable today. 1977 had no internet, no mobile phones, no personal computers in any meaningful sense. Engineers did their calculations with slide rules and mainframe terminals. The Apollo program had ended just a few years earlier. The space shuttle hadn't flown yet, and in the middle of all that, NASA was quietly planning something far more ambitious than putting humans on the moon. They were planning to send machines to the edge of the solar system and beyond. What made it possible was an accident of celestial geometry. Every 176 years, the 4 outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, align in a configuration that allows a spacecraft to visit all 4 using a technique called gravitational assist. The idea is elegant. Instead of carrying enough fuel to fly directly to each planet, a spacecraft can use each planet's gravity like a slingshot, stealing a small amount of the planet's orbital momentum to accelerate itself toward the next target. Without this alignment, visiting all 4 outer giants would require multiple separate missions, decades of planning, and far more fuel than any rocket could carry. The alignment window opened in the late 1970s. It would not open again until 2153. NASA recognized the opportunity and seized it. The Grand Tour was born. Jupiter, Saturn, Uranus, Neptune, 4 worlds in a single journey. Scientists mapped the trajectories, calculated the gravity assists, designed the instruments, and launched 2 spacecraft within 2 weeks of each other. Everything went according to plan. But here is the thing nobody planned for. The greatest discoveries made by Voyager 1 and Voyager 2 did not come from the planets. They did not come from Jupiter's storms or Saturn's rings or Neptune's winds. They came from something far beyond all of those worlds, from a boundary that scientists thought they understood, a line they had drawn on their models with confidence, a place they had calculated down to the last astronomical unit. They were wrong about almost everything, and the proof of that was transmitted home in a signal weaker than a nightlight crossing. 17 billion kilometers of darkness, arriving after a 22-hour journey, a message from the edge of everything, rewriting the map of our cosmic neighborhood, one instrument reading at a time. 2 metal boxes, built with 1970s technology, designed to last 5 years, still talking to us nearly 50 years later, still surprising us, still teaching us things we did not know. If you could send one object beyond the solar system to represent everything humanity is, what would you choose? Before Voyager could reach the edge, it had to pass through the planets, and the first world it encountered was nothing like anyone expected. The discovery waiting at Jupiter was so shocking that the engineer who found it almost didn't believe her own eyes. Nobody expected Jupiter to look like that. Before Voyager, the best images of Jupiter came from ground-based telescopes. Scientists could see the broad cloud bands, the general structure, the hint of the Great Red Spot. But the resolution was low, the details were blurred, and most of what was known about Jupiter came from inference and theory, rather than direct observation. Scientists knew it was large, they knew it rotated fast, they knew the cloud bands were real. Beyond that, the picture was incomplete. Voyager 1 reached Jupiter in March of 1979. What the cameras sent back rewrote everything. The Great Red Spot, known to astronomers since the 1600s, observed through telescopes for 3 centuries, turned out to be something far more dramatic than anyone had calculated. It is an anticyclone, a high-pressure storm rotating counterclockwise, rising approximately 8 kilometers above the surrounding cloud layer. The storm is wider than Earth. It has been spinning continuously for at least 350 years, possibly much longer, and it shows no sign of stopping. Wind speeds within the storm reach 500 kilometers per hour. The structure visible in Voyager's images, the swirling interior bands, the complex edge dynamics, the intricate layering was nothing like the smooth oval that telescopes had suggested. Surrounding the Great Red Spot, the atmosphere of Jupiter revealed itself as a system of staggering complexity. Dozens of smaller storms, each larger than a major hurricane on Earth, moved through the cloud bands in patterns governed by Jupiter's rapid rotation. The planet completes one full rotation in just under 10 hours, less than half the time Earth takes despite being 11 times wider. That rotation generates powerful forces that organize the atmosphere into alternating jets of east-flowing and west-flowing wind, creating the banded structure visible from space and the violent turbulence that drives everything within it. Then there was the lightning. Jupiter has lightning. That much was expected. What was not expected was the scale. A single lightning bolt in Jupiter's atmosphere releases roughly 1,000 times more energy than a typical bolt on Earth. And this lightning is not rare. It is constant. It is happening everywhere, all the time, deep in the cloud layers, illuminating the atmosphere from below in continuous flickers of tremendous energy. The electromagnetic signatures of these bolts were detected by Voyager's instruments long before the planet came into visual range, a crackling, stormy roar from the largest planet in the solar system. But neither the storms nor the lightning was the discovery that stopped the mission team cold. That discovery came from Io. Io is the innermost of Jupiter's 4 large moons. Before Voyager, scientists expected it to look something like Earth's moon, cratered cold, geologically dead, a frozen record of ancient bombardment. A navigation engineer named Linda Morabito was processing images from the Io flyby, looking for reference stars to precisely determine Voyager's position when she noticed something unusual in the frame. A strange umbrella-shaped plume extending beyond the edge of Io's visible surface. She looked at it for a long time. She checked the data. She ran the numbers again. It was a volcanic eruption, active, ongoing, enormous, a plume reaching nearly 300 kilometers above the surface. And it was not alone. As the team analyzed the full image set from the Io flyby, they found 9 active volcanoes. Not ancient, not dormant, active, erupting, reshaping the surface in real time. Io turned out to be the most volcanically active body in the entire solar system. More than 400 volcanic centers have since been catalogued on its surface. The landscape is constantly being resurfaced by flows of sulfur and silicate lava, which is why Io has almost no impact craters. The surface is too young. Any crater that forms gets buried under new volcanic material within a geologically brief period. The colors of Io, the yellows, oranges, reds, and blacks, come from different forms of sulfur deposited by this endless eruption cycle. What powers all of this? Gravity. Jupiter is so massive, and its gravitational pull on Io is so intense that the tidal forces generated by Jupiter, combined with gravitational tugs from the neighboring moons, Europa and Ganymede constantly flex and deform Io's interior. The moon is being squeezed and stretched as it orbits like a rubber ball being repeatedly compressed. That mechanical deformation generates heat. The heat melts rock. The molten rock erupts. The process never stops because the orbital mechanics never stop. This was a new idea about how worlds work. Before Voyager, geologists assumed that volcanic activity required either radioactive decay, heating a planet's interior, or residual heat from formation. Tidal heating volcanic activity driven by gravitational squeezing from an external body was theoretical. Io made it real, and the implications extended far beyond Jupiter. If tidal heating can drive volcanism on Io, it can do the same on Europa, on Saturn's moon Enceladus, and potentially on rocky moons orbiting giant planets in other solar systems entirely. Europa presented a different kind of mystery. Its surface is ice-smooth, bright and crisscrossed with an intricate network of cracks and ridges. The cracks stretch for hundreds of kilometers, running parallel and intersecting in patterns that look almost geological, like something moving beneath the surface and pushing the ice apart from below. Crucially, Europa has almost no impact craters. A surface without craters is a young surface, one that is being continuously renewed. Something beneath the ice is active. The implication was profound. If Europa's ice shell is being cracked and renewed from below, there might be liquid water beneath it. An ocean kept from freezing by the same tidal heating mechanism that powers Io's volcanoes, though gentler enough to keep water liquid rather than melt rock entirely. An ocean, larger by some estimates than all the oceans of Earth combined, sealed beneath kilometers of ice, isolated from the rest of the solar system, potentially for billions of years. Voyager could not prove that ocean existed. The evidence was circumstantial, but the possibility was enough to make Europa one of the most important targets in the search for life beyond Earth, a title it still holds today. Jupiter also turned out to have rings, faint thin, made of dust-sized particles rather than ice. Nothing like Saturn's spectacular system, but rings nonetheless. No telescope had detected them from Earth. Voyager 1 confirmed their existence during the Jupiter flyby. It was a reminder that the solar system contains structures and phenomena that our best instruments pointed from one small planet simply could not see. Scientists had named Jupiter's moons after figures from Greek and Roman mythology who were seduced or transformed by Zeus, the god Jupiter, in the Roman tradition. Io, Europa, Ganymede, Callisto. In other words, Jupiter is literally surrounded by the victims of its own mythological counterpart. The largest planet in the solar system, king of the gods, encircled by the consequences of its own gravitational dominance. The mythology turned out to be more accurate than anyone intended. If life exists in the ocean beneath Europa's ice, what do you think it looks like? Jupiter was only the opening act. What waited at the next stop in Voyager's journey was so beautiful, so intricate, and so structurally impossible that physicists had to rebuild their models of how matter behaves when gravity shapes it. What Voyager found at Saturn changed the way we understand rings, moons, and the mechanics of order in a chaotic universe. Saturn has been observed since ancient times. Even without a telescope, it is visible to the naked eye as a bright, steady point of light in the night sky. But it was not until the 1650s that the Dutch astronomer Christiaan Huygens finally understood what he was seeing, that the strange oval shape around Saturn, which Galileo had described as ears or handles when he first observed it, through his rudimentary telescope, was in fact a ring, surrounding the planet. By the time Voyager launched in 1977, scientists knew Saturn had multiple rings. They had mapped the A ring, the B ring, the C ring, and the Cassini division, a large gap between the A and B rings whose origin was explained by orbital resonance with the moon Mimas. They had a reasonable picture. Several distinct rings, a few notable gaps, a structure that could be modelled and explained with the physics available. Voyager arrived at Saturn in November of 1980 and sent that picture to pieces. What What the cameras revealed was not a few distinct rings separated by gaps. It was thousands of individual ringlets, narrow bands of material packed together so densely that the overall structure looked less like a planetary ring system and more like the grooves on a vinyl record. Each one a separate track, each one governed by its own specific orbital mechanics. The apparent simplicity of Saturn's rings observed from Earth had hidden an architecture of extraordinary complexity. The rings are simultaneously vast and impossibly thin. They extend outward from Saturn for hundreds of thousands of kilometers wide enough to stretch most of the way from Earth to the Moon. But their thickness in most places is roughly 10 meters. 10 meters. If you were to scale Saturn's ring system down to the size of a standard sheet of paper, the rings would be thinner than the paper itself. A structure wider than the distance between cities, thinner than a human body held in that impossible geometry by nothing but the precise balance of orbital mechanics and particle collisions. Every individual piece of material within the rings is in its own way a tiny moon. Each fragment of ice and rock follows its own orbit around Saturn, moving at a speed determined by its distance from the planet according to the same gravitational laws that govern the Moon's orbit around Earth. What makes the rings a ring, rather than a cloud of independent debris, is that all of these billions of particles are confined to the same extremely thin plane, a consequence of the collisions between them that have gradually flattened the POW system over millions of years. Order emerging from chaos, one collision at a time. Voyager revealed structures within the rings that nobody anticipated. Density waves, patterns of alternating, compressed and sparse material, spiral through the rings like sound waves through air generated by gravitational resonances with Saturn's moons. Where ring particles orbit at precise fractional ratios to a moon's orbital period, the repeated gravitational nudges from that moon amplify into visible waves that ripple through the ring material in elegant spiral patterns. The physics governing these waves is the same physics that governs spiral galaxies. Saturn's rings turned out to be a natural laboratory for understanding how gravity sculpts matter at scales, from the microscopic to the galactic. The F-ring, one of the outermost distinct rings, showed something even stranger, a braided structure, multiple strands appearing to wind around each other in a pattern unlike anything else in the solar system. The explanation came from two small moons, Prometheus and Pandora, orbiting just inside and just outside the F-ring respectively. Their gravitational influence continuously perturbs the ring particles, pulling material into strands, creating the braided appearance and preventing the ring from dispersing. They are shepherd moons, keeping the flock of particles corralled through gravity alone as reliably as any physical barrier. Titan, Saturn's largest moon, received a dedicated close approach. Voyager 1 flew within 2,500 kilometers of its surface, so close that the flyby permanently altered the spacecraft's trajectory, preventing it from continuing to Uranus and Neptune. That sacrifice was made deliberately. Scientists judged Titan important enough to warrant it, and the data came back confirming that judgment. Titan's atmosphere is thicker than Earth's. The surface pressure is approximately 1.5 times the pressure at sea level on Earth, higher than any other moon in the solar system, exceeded only by Venus among all solid bodies. The composition is primarily nitrogen, roughly 95%, with methane and other organic compounds making up the rest. When sunlight breaks down those hydrocarbons in the upper atmosphere, it creates complex organic molecules called tholins, reddish-brown particles that form a dense, impenetrable haze layer and give Titan its characteristic orange color. The surface was completely invisible from Voyager's cameras. What lay beneath that haze would remain unknown for another 25 years. What made Titan genuinely extraordinary was the chemistry happening in its atmosphere. The same organic reactions that Titan's atmosphere runs continuously, sunlight breaking down methane into complex hydrocarbons. Those hydrocarbons reacting further, building larger and more complex molecules, are similar in principle to the reactions believed to have produced the building blocks of life in Earth's early atmosphere. Titan is doing prebiotic chemistry at minus 180 degrees Celsius, slowly, steadily, in the dark beneath its haze. It is a natural chemistry experiment running on a planetary scale, and it has been running for billions of years. After Saturn Voyager, 2 continued alone toward the ice giants. Uranus, in January of 1986, revealed a planet tilted so dramatically to 98 degrees relative to its orbital plane that it essentially rolls along its orbit on its side, with its poles pointing roughly toward and away from the Sun rather than its equator. Each pole endures 42 years of continuous daylight, followed by 42 years of unbroken darkness. Miranda, one of Uranus's moons, displayed terrain so chaotic, ancient cratered plains sitting directly adjacent to young grooved terrain. Enormous cliffs rising 10 kilometers from the surface that scientists spent years debating whether it had been shattered by a catastrophic impact and reassembled from the fragments. Neptune, in August of 1989, delivered the final surprise of the planetary mission. A world expected to be quiet and featureless turned out to have the most violent atmosphere of any planet Voyager visited. Wind speeds exceeding 2,100 kilometers per hour, the fastest measured anywhere in the solar system, howling across a planet with a surface temperature of minus 220 degrees Celsius. The Great Dark Spot, an Earth-sized storm, rotated in Neptune's southern hemisphere. Triton, Neptune's largest moon, orbited in the wrong direction, retrograde opposite to Neptune's own rotation, a clear sign that it was not born alongside Neptune, but captured from the Kuiper Belt. And on Triton's surface, at one of the coldest temperatures recorded anywhere in the solar system, geysers of nitrogen gas erupted through the surface, carrying dark particles kilometers into the sky. The planetary mission was over. 4 giants, dozens of moons, rings and storms and geysers and hidden oceans. More discoveries in 12 years than all previous outer solar system observations combined. The spacecraft was still operational, still transmitting, still capable of science, and ahead of them lay something no instrument had ever measured, no spacecraft had ever reached, and no model had ever gotten right. Titan has organic chemistry, rain, and rivers. Does that feel like enough for life to exist there, or does life need something more? Voyager had conquered every planet on its path. But the real journey, the one nobody planned for, the one that would rewrite the textbooks, was only just beginning. Because what waited beyond the planets was a boundary that scientists had mapped in detail, calculated with confidence, and described in papers for decades. And Voyager was about to show them exactly how wrong they were. The Sun is dying. Slowly, quietly, invisibly losing mass at a rate that would seem catastrophic if you watched it happen on a human timescale. Every single second, the Sun sheds approximately 1 million tons of itself into space. Not as light, not as heat, as matter, a continuous stream of charged particles, protons, electrons, helium, nuclei, accelerating outward from the solar corona in every direction, simultaneously filling the entire solar system with a relentless, invisible wind. This is the solar wind. It travels at speeds between 400 and 800 kilometers per second. It is a plasma, a state of matter so hot that electrons have been stripped completely from their parent atoms, leaving behind a soup of charged particles moving faster than any conventional aircraft, faster than any rocket humanity has ever built, flowing outward without pause, without interruption, every hour of every day since the Sun first ignited roughly 4.5 billion years ago. In 1958, a physicist at the University of Chicago named Eugene Parker published a theoretical paper predicting that this solar wind existed. His argument was based on the physics of the Sun's outer atmosphere, the corona, which he showed was so extraordinarily hot that its gas could not be held in place by the Sun's gravity. The corona had to be leaking continuously into space. The solar wind was not a storm phenomenon. It was not occasional. It was permanent, structural, inevitable. The scientific community responded with ridicule. Referees rejected his paper. Colleagues told him the idea was physically impossible. The interplanetary medium was assumed to be essentially empty, a hard vacuum between the planets disturbed only by occasional bursts from solar flares. A continuous wind flowing outward at hundreds of kilometers per second was considered implausible by most experts in the field. 3 years later, spacecraft measurements confirmed Parker was right about everything. The solar wind is real. It is continuous. It flows at exactly the speeds he predicted. And every day since that confirmation, the Sun has been pushing it outward, a river of plasma expanding through the solar system in all directions, carrying the Sun's magnetic field with it, filling an enormous bubble of space with solar, T material. That bubble is called the heliosphere. Its outer boundary, the place where the solar wind finally loses the battle against the pressure of interstellar space and can expand no further, is called the heliopause. And everything inside that boundary, from Mercury's orbit to the furthest reaches of the solar wind's influence, belongs to the Sun in a very real physical sense. The heliosphere is the Sun's domain. Before the solar wind reaches the heliopause, it encounters a transition zone called the termination shock. The solar wind is supersonic, moving far faster than the speed at which pressure waves can travel through the plasma. In the inner solar system, the wind travels at roughly 10 times the local sound speed. When any supersonic flow encounters a large-scale obstacle, physics requires that a shockwave form ahead of that obstacle. At the termination shock, the solar wind abruptly slows from supersonic to subsonic speeds, compresses, heats up dramatically, and becomes turbulent. Beyond that shock, the slowed and heated plasma fills a region called the heliosheath, a thick, churning transition zone between the supersonic solar wind and the heliopause itself. Beyond the heliopause lies interstellar space, the space between stars, a medium so thin it makes the best vacuum humans have ever created in a laboratory look dense by comparison, roughly 0.1 atoms per cubic centimeter, about 10 million billion times less dense than the air at sea level. Yet not empty, that tenuous gas has pressure, it has momentum, and the Sun moving through it at roughly 490,000 kilometers per hour, relative to the local interstellar medium, creates a situation analogous to a boat moving through water, compressed ahead, stretched into a long tail behind. Through the 1980s and 90s, teams of physicists built sophisticated computer models of this entire system. They ran three-dimensional magnetohydrodynamic simulations, incorporating the solar wind's known properties, the estimated density and pressure of the interstellar medium, the Sun's velocity through that medium, and the complex behavior of plasma in the presence of magnetic fields. These were serious, rigorous models, built by serious, rigorous scientists, using the best available data and decades of accumulated understanding. The models produced a clear picture. The termination shock should lie somewhere between 75 and 90 astronomical units from the Sun. 1 astronomical unit being the average distance from Earth to the Sun, approximately 150 million kilometers. The heliosheath beyond it should be roughly 10 to 20 astronomical units thick. The heliopause should sit at approximately 90 to 100 astronomical units. Beyond the heliopause, galactic cosmic rays, high-energy particles accelerated by supernova explosions and other violent events across the galaxy, would increase sharply in intensity, no longer blocked by the solar wind's magnetic influence. The transition across the heliopause should be relatively quick, a matter of weeks to months at most. The shape should be roughly spherical, perhaps slightly elongated in the direction opposite the Sun's motion, a modest asymmetry, a minor correction to an otherwise symmetric bubble, nothing dramatic. The models all agreed on this. The equations were well established, the physics was solid, the calculations had been checked and rechecked. By 2004, as Voyager 1 approached the predicted location of the termination shock, scientists spoke with genuine confidence. The spacecraft was approaching a boundary they had mapped from a distance. They knew within reasonable margins what it would find there, where it would find it, and what the crossing would look like. That confidence was about to meet reality, and reality had other plans entirely. The interstellar medium pressing against the heliopause from outside contained something that the models had estimated but never directly measured: galactic cosmic rays. These are not the gentle radiation of sunlight. They are particles, mostly protons, accelerated to extraordinary energies by the most violent events in the galaxy. A single high-energy cosmic ray can carry more kinetic energy than a thrown baseball concentrated into a single subatomic particle. The heliosphere acts as a partial shield against these particles. The solar wind's magnetic field deflects and slows many of them before they reach the inner planets. Models predicted that cosmic ray intensity would roughly double or triple once a spacecraft crossed the heliopause into unshielded interstellar space. Everything seemed to fit. The termination shock, the heliosheath, the heliopause, the cosmic ray gradient, a coherent, self-consistent picture assembled from decades of careful theoretical work. When Voyager reached the predicted boundary zone, the instruments would simply confirm what the models described. When every model agrees, when the best scientists in the field reach the same conclusion, does consensus make something true? Voyager 1 flew straight toward the point science had already marked on the map, but when it arrived at the coordinates where the boundary was supposed to be, there was nothing there. And what was truly waiting further ahead existed on no map ever drawn. On August 1st, 2002, Voyager 1's instruments registered something unexpected. The spacecraft was at 85 astronomical units from the Sun, already beyond the inner edge of the predicted termination shock zone, when it detected the signatures of a shock crossing. The solar wind appeared to slow, plasma density increased. The magnetic field shifted. Everything looked like a termination shock encounter. Then it reversed. Over the following months, the boundary moved. The shock signatures faded. Voyager found itself back in the familiar supersonic solar wind, as if the termination shock had retreated outward past the spacecraft. In 2003, the signatures appeared again, the shock washing over Voyager a second time as the boundary oscillated. Then, retreating again. The termination shock was not a fixed line in space. It was breathing, expanding, and contracting in response to variations in solar activity, pushed outward by strong bursts of solar wind, pulled inward when activity dropped. A boundary that moved sometimes by several astronomical units on timescales of months. Finally, on December 16th, 2004, Voyager 1 made the definitive crossing. The spacecraft was at 94 astronomical units from the Sunday. Every model had predicted the termination shock would lie between 75 and 90 astronomical units. Voyager had already passed through the entire predicted range without finding it. The boundary was farther than any model had calculated, and the crossing itself spread across multiple events over 2 years, rather than happening in a single clean encounter, was nothing like the simple transition scientists had described, but the real shock came 2 years and 8 months later. Voyager 2 crossed the termination shock on August 30th, 2007. The crossing happened at 84 astronomical units from the Sunday, nearly 10 astronomical units, roughly 930 million kilometers closer to the Sun than where Voyager 1 had crossed. 2 spacecraft, 2 crossings, a distance difference of 930 million kilometers between them. If the heliosphere was spherical, both spacecraft should have crossed the termination shock at roughly the same distance from the Sun, regardless of direction. The fact that they didn't was the first hard evidence of what the models had missed. The heliosphere is not a sphere. It is compressed in the direction the Sun is moving through the interstellar medium. The leading face called the nose, where interstellar pressure bears down most directly. It is extended outward in other directions, stretched into something more like a teardrop or a bullet shape, with a long tail streaming behind the Sun's direction of travel. Voyager 1 was heading roughly toward the nose. Voyager 2 was traveling toward the side. The nose is compressed by the Sun's motion, just as the front of a boat is pushed against the water while the wake spreads out behind it. The Sun moves through the local interstellar medium at roughly 490,000 kilometers per hour. That motion creates a headwind from the perspective of the heliosphere, compressing the forward face and stretching the tail into the distance. The 2 Voyagers were sampling different parts of a structure that was neither symmetric nor static. After crossing the termination shock, both spacecraft entered the heliosheath, the turbulent transition zone that models said would be 10 to 20 astronomical units thick and would take 5 to 10 years to cross. Scientists calculated that Voyager 1 should reach the heliopause around 2015 at approximately 100 to 110 astronomical units. Starting in 2010, something unexpected began to happen. Voyager 1's instruments started detecting increasing levels of galactic cosmic rays. Not the sharp jump expected at the heliopause, a gradual rise building over months, while the spacecraft was still clearly inside the heliosheath. Solar particles were simultaneously fading. Both of these changes were supposed to happen at the heliopause, not in the middle of the heliosheath. The boundary was doing something the models had never described. In June of 2012, Voyager 1 found something that had no name because nobody had predicted it could exist. A region where the magnetic field lines aligned in a perfectly radial direction pointing straight outward from the Sun, organized and smooth in a system that should have been turbulent and tangled. Along these field lines, particles were streaming in both directions simultaneously. solar particles flowing outward, galactic cosmic rays flowing inward. The field lines were acting as a direct connection between the heliosheath and interstellar space, a highway cutting straight through the boundary, allowing particles to flow freely both ways, as if the heliopause at this location had been replaced by an open corridor. Scientists called it the magnetic highway. No model predicted it. No theoretical framework had suggested it could exist. The leading explanation is that the Sun's magnetic field lines were connecting directly to galactic field lines. At this location, a process called magnetic reconnection, creating open pathways through what was supposed to be a closed boundary. Voyager 1 spent approximately 2 months traveling through this corridor, detecting cosmic ray levels higher than anywhere else in the heliosheath, while solar particle counts dropped steadily towards zero. Then, on August 25, 2012, everything changed at once. Solar wind particles essentially vanished. Cosmic ray intensity jumped to a high, steady level within a matter of days. By 2 measures out of 3, Voyager 1 appeared to have crossed the heliopause and entered interstellar space. But the magnetic field did not rotate. At the heliopause, the Sun's magnetic field should give way to the galactic magnetic field, which was expected to point in a significantly different direction. The field rotation was supposed to be one of the clearest, most unambiguous signs of a heliopause crossing. Instead, the field kept pointing the same way it had been pointing throughout the heliosheath. The debate that followed lasted more than a year. Some scientists argued the crossing was real. Others argued that without a field rotation, the spacecraft must still be inside the heliosphere, perhaps in some previously unknown intermediate layer. In September of 2013, NASA settled the debate officially. Voyager 1 had crossed the heliopause on August 25, 2012. The spacecraft was at 121 astronomical units from the Sun, approximately 17 billion kilometers. The reason the magnetic field had not rotated turned out to be a coincidence of cosmic geometry. The galactic magnetic field in that specific region of space happens to point in nearly the same direction as the Sun's field. Not because they are connected, but because the local interstellar medium has its own structure, that at Voyager, one's crossing point happened to align with the solar field, a coincidence that caused more than a year of scientific confusion. The heliopause was not at 90 to 100 astronomical units. It was at 121, nearly 4 billion kilometers beyond the furthest edge of every prediction. The heliosphere is larger than science believed, which means its shielding effect against galactic cosmic rays is stronger than calculated, which means the radiation environment at Earth over geological timescales has been different from what the models assumed, which means questions about cosmic ray, influences on climate, atmospheric chemistry, and biological mutation rates all need to be revisited. Voyager 2 crossed the heliopause on November 5, 2018 at 119 astronomical units. 2 crossings, 2 directions, 2 data points, confirming that the heliosphere's actual shape does not match the model's asymmetric, in ways the models did not predict, dynamic in ways the models treated as negligible, structured at its boundary in ways nobody had imagined. 7 major discoveries lay ahead. This was only the first. And the most disorienting surprises were waiting in the space beyond the boundary in the interstellar medium itself, in measurements that would force scientists to confront how little they truly understood about the environment surrounding our solar system. If the boundary of the solar system turned out to be 40% farther than every model predicted, what does that say about the other things we are certain we understand? That was only the first of 7 shocks. Because when Voyager finally stepped into true interstellar space and began taking direct measurements of what exists out there, the numbers it sent back forced scientists to start over from the beginning. For the entire history of astronomy, every piece of knowledge about interstellar space came from a distance. Spectroscopy analyzing the light from distant stars as it passed through the interstellar medium and left chemical fingerprints in the spectrum. Radio observations detecting hydrogen clouds emitting at specific wavelengths across the galaxy. Theoretical models building mathematical descriptions of how the medium should behave based on physical laws and indirect measurements. All of it was inference. All of it was observation from afar, like trying to understand the ocean by studying waves on a beach and never once putting your hand in the water. On August 25th, 2012, that changed permanently. When Voyager 1 crossed the heliopause and its instruments began returning readings from the other side, humanity had done something it had never done before in the entire span of its existence. It had put instruments directly into interstellar space and taken measurements, not estimates, not calculations based on observations from 121 astronomical units away. Direct readings, physical contact with the medium between the stars. The first measurement that came back was density. The interstellar medium surrounding our solar system contains approximately 0.08 particles per cubic centimeter. To put that number in context, the best vacuum chamber ever built on Earth, the most sophisticated laboratory apparatus, specifically engineered to remove as many molecules as possible from an enclosed space, achieves a density of roughly 1 million particles per cubic centimeter. Interstellar space is more than 10 million times emptier than the emptiest environment human technology has ever produced. By any reasonable definition, it is a vacuum more perfect than anything we can manufacture, and yet it is not empty. 0.08 particles per cubic centimeter means that in any given cubic meter of interstellar space, there are approximately 80,000 particles. Not nothing, not zero. 80,000 individual atoms or ions drifting through the void, separated from each other by distances that dwarf anything in our daily experience but present nonetheless. And it is the collective pressure of these 80,000 particles per cubic meter, multiplied across the incomprehensible volume of space surrounding the heliosphere, that is sufficient to hold the solar wind at bay. The solar wind, which carries 1 million tons of material away from the sun every single second, traveling at up to 800 kilometers per second, is stopped dead at 121 astronomical units by a medium so thin that our best technology cannot replicate it. The temperature reading was more disorienting. Voyager's instruments measured the interstellar medium at temperatures ranging from roughly 30,000 to 50,000 degrees Celsius. That sounds like a furnace. It sounds incompatible with a region described in the same breath as being colder than anything imaginable. But temperature in a plasma is not the same as heat in any practical sense. Temperature measures the average kinetic energy of individual particles, how fast they are moving. In the interstellar medium, individual particles are moving very fast, but they are so extraordinarily far apart from each other that the actual transfer of thermal energy between them is negligible. A spacecraft traveling through this region would not be heated by the plasma around it. There are simply not enough particles per unit volume to deliver any meaningful amount of energy through collision. An astronaut exposed to interstellar space would freeze to death, not burn, despite being surrounded by plasma, nominally measured at tens of thousands of degrees. The pressure was measured at approximately 3 times 10 to the power of negative 12 pascals. The atmospheric pressure at sea level on Earth is 101,000 pascals. The pressure of interstellar space is roughly 100 trillion times smaller than the air pressing on your skin right now. It is a number so small, it is essentially impossible to intuit. And yet again, that pressure is sufficient. It balances the solar wind. It defines the heliopause. The most powerful sustained outflow in the solar system is ultimately stopped by something that registers as effectively zero on any pressure gauge designed for human-scale environments. The galactic magnetic field came in at approximately 0.05 nanotesla. Earth's magnetic field at the surface measures around 50,000 nanotesla, 1 million times stronger. The field threading through the interstellar medium near our solar system is so weak that it would be completely undetectable by any instrument not specifically engineered to find it. But it extends across thousands of light years without interruption. It permeates the entire local galaxy. It guides the trajectories of charged particles across interstellar distances. And its orientation, which direction it points in the region just outside our heliopause, turned out to be one of the most scientifically significant and confusing measurements. Voyager returned a story that belongs to the next part of this account. Every one of these numbers differed from the model predictions. Not catastrophically. The models were not wildly wrong in the way that a flat Earth map is wrong about the shape of continents. The physics was correct. The basic framework was sound, but the specific values, the actual density, the actual temperature, the actual pressure, the actual field strength, all came back slightly different from what 40 years of theoretical work had calculated. The density was a bit higher than estimated in some regions, a bit lower in others. The temperature was in the right range, but at the high end of predictions. The magnetic field strength was broadly consistent, but the orientation was entirely unexpected. Each small discrepancy taken in isolation might seem like a minor calibration issue, but these are not isolated numbers. They feed into each other. A slightly higher interstellar density means slightly more pressure on the heliopause, which changes the heliopause distance, which changes how much cosmic ray shielding the heliosphere provides, which changes the flux of high-energy particles reaching Earth's upper atmosphere over geological timescales. Cosmic rays produce carbon-14 in the atmosphere, the isotope used in radiocarbon dating. They influence the chemistry of the upper atmosphere. They may affect cloud formation. Over millions of years, variation in cosmic ray flux, driven by changes in the interstellar medium, could affect mutation rates, evolutionary pressures, the pace of biological change on Earth's surface. The interstellar medium is not an abstraction. It is a physical environment that has been shaping life on Earth since life began, silently and invisibly through the medium of radiation. After 40 years of building the most sophisticated plasma physics models the field had ever produced, after running simulations on the most powerful computers available and refining the parameters across hundreds of published papers, Voyager 1 arrived at the destination and reported back that everything was slightly off. It is objectively the most polite way the universe has ever told us that we had almost entirely miscalculated. If the density of the interstellar medium directly shapes how much cosmic radiation reaches Earth, does the Sun's position within the galaxy play a role in making life here possible? But the strangest discovery was not the numbers being wrong. It was something Voyager heard. Pressure waves rolling outward from a star, billions of kilometers behind it, crossing the heliopause and propagating through interstellar space like tsunamis moving through an ocean nobody knew existed. In October of 2012, Voyager 1's plasma wave instrument detected something moving through the interstellar medium around it. Not a particle, not a change in the magnetic field direction. A wave, a compression moving through the plasma, a region of slightly increased density, traveling outward from the direction of the Sun, passing over the spacecraft like a ripple crossing the surface of a still pond. The instrument that detected it measures oscillations in plasma, the tiny vibrations that charged particles undergo when disturbed by a passing wave. From the frequency of those oscillations, scientists can calculate the local electron density with precision. What Voyager 1 detected in October and November of 2012 was a coherent, organized wave structure propagating through the interstellar medium at a measurable speed. It lasted for several weeks, then it faded. The interstellar plasma settled back to its background state. Tracing the wave backward following its origin in time and direction, scientists identified the source. In 2012, the Sun had produced a series of powerful eruptions, coronal mass ejections, enormous bursts of magnetized plasma launched outward from the solar surface at millions of kilometers per hour. Those eruptions sent powerful pulses racing outward through the heliosphere. The pulses traveled for years, crossing the heliosheath, building energy as they compressed the plasma ahead of them. When they reached the heliopause, they struck the boundary like a hammer striking a drum. The impact launched a shock wave into the interstellar medium, a compression pulse propagating outward through a medium the solar wind itself could not enter. That compression wave, born from a solar storm, traveled through interstellar space at approximately 60 kilometers per second. Slower than the solar wind, slower than the original eruption, but fast enough to cover several astronomical units per year, fast enough to reach Voyager 1 and register on its instruments months after crossing the heliopause. The solar storm that generated it had occurred years before the detection. The wave had been traveling through interstellar space the entire time, invisible and unmeasured, until Voyager 1 happened to be in its path. A second tsunami arrived in April and May of 2013. Different frequency, indicating a slightly different electron density at Voyager's new position. The spacecraft had moved farther from the Sun in the intervening months, and the medium had changed subtly. A third wave passed through in March of 2014. A fourth was detected in 2015, each one traced back to a distinct solar event. Each one provided a new measurement of local interstellar electron density. Each one confirmed that what Voyager was experiencing was not an artifact, not an instrument malfunction, not a coincidence, but a repeating physical phenomenon of genuine scientific importance. The significance of this discovery is difficult to overstate because it demolished one of the foundational assumptions underlying every model of the heliosphere ever built. Every model treated the heliopause as a one-way boundary. In a specific sense, solar wind plasma stays inside, interstellar medium stays outside, and the two regions are essentially sealed from each other, except for the gradual pressure, equilibrium that defines the boundary's position. The heliopause was modeled as a hard wall, a surface where one medium ends and another begins, like the surface of the ocean, dividing water from air. The tsunami detections showed it is nothing of the kind. The heliopause is not a wall. It is a membrane, a dynamic vibrating surface that transmits energy across its boundary in the form of pressure waves. A solar storm happening inside the heliosphere can generate a disturbance that crosses the heliopause and propagates through interstellar space for an unknown distance beyond. The sun's influence does not end at the heliopause. It reaches further, carried not by matter but by the physics of wave propagation through a continuous medium. The image that clarifies this is simple. Imagine dropping a stone into a still pond. The stone hits the water and sinks. Its physical influence, its mass, its momentum is confined to the point of impact, but the energy it carries propagates outward as waves on the surface, moving in expanding rings that travel far beyond where the stone entered the water. The stone is the coronal mass ejection. The pond is the heliosphere. The waves on the surface are the pressure pulses that cross the heliopause and continue into interstellar space. The stone itself, the solar plasma, never leaves the pond, but the waves it creates travel on without it. No model had predicted this, not one. The theoretical literature on the heliopause, accumulated over decades, uniformly described it as a region where solar influence terminates, not reduces, not attenuates, terminates. The discovery of solar tsunamis propagating through interstellar space required a fundamental revision of that picture, not of the underlying physics, which is perfectly consistent with wave propagation across boundaries, but of the assumption that anyone had bothered to apply that physics to this particular boundary in this particular way. There is a broader implication that extends beyond our own solar system. Every star produces a solar wind. Every solar wind creates a heliosphere around its parent star. Every heliosphere has a heliopause, and every solar storm on every star will generate pressure waves that cross that heliopause and propagate into the interstellar medium between the stars. The space between stellar systems is not silent. It is filled with waves, pressure pulses from billions of stars crossing and interfering and fading across the light years, an invisible acoustic landscape that pervades the galaxy. Voyager 1 detected our sun's contribution to that landscape. It was the first instrument ever to do so, and it did it using a plasma wave detector built with 1970s technology on a spacecraft that was never designed to reach interstellar space in the first place. The sun reaches further than we imagined, not with matter, with waves. With the physical memory of storms that happened years ago and billions of kilometers away still propagating outward through a medium the sun's material will never touch. If the sun sends pressure waves across the heliopause and into interstellar space, they could all the stars in the galaxy be exchanging these waves, continuously filling the void between them with signals nobody has learned to read yet. The FD. Tsunamis revealed the sun is more powerful than we believed. But a larger mystery was still waiting, one where even the direction of the magnetic field refused to follow the script, and where the map of the galaxy's own structure turned out to be written in a language the models had never quite learned to read. When a spacecraft crosses from one region of space into a fundamentally different one, the magnetic field should announce that transition clearly. This was not a controversial expectation. It was basic physics built into every model of the heliopause ever constructed, confirmed by theoretical reasoning from multiple independent directions. The sun generates its own magnetic field. That field is carried outward by the solar wind, stretched and twisted by the sun's rotation, into a vast spiral structure filling the entire heliosphere. The galaxy has its own magnetic field, ancient, large-scale, shaped by the collective motion of billions of stars and the currents of plasma that flow through the interstellar medium across thousands of light years. These two fields belong to fundamentally different systems. Where one ends and the other begins, the compass should turn. At the heliopause crossing on August 25, 2012, Voyager 1's magnetometer recorded no such turn. The field direction before the crossing and the field direction after it were essentially identical, not approximately the same, not rotated by a small, measurable angle. The same direction within the precision of the instrument, pointing the same way it had been pointing throughout the heliosheath for years prior. If a scientist looked only at the magnetometer data from Voyager 1, without knowing anything else about the crossing, they would see no signal indicating that anything significant had changed. The most fundamental expected signature of a heliopause crossing the rotation of the magnetic field from solar-dominated to galaxy-dominated orientation was simply absent. This is what drove more than a year of genuine scientific controversy following August 25, 2012. The plasma data said the crossing had happened. The cosmic ray data said the crossing had happened. The magnetic field data said nothing had changed. These three things could not all be simultaneously true under any model that existed at the time. Something was wrong either with the crossing interpretation, or with the models, or with an assumption so deeply embedded in the theoretical framework that nobody had thought to question it. The resolution came gradually assembled from careful analysis of data from multiple instruments over many months. The galactic magnetic field in the specific region of the local interstellar medium, where Voyager 1 made its crossing, happens to point in nearly the same direction as the Sun's magnetic field at that location. Not because the fields are connected, not because some physical mechanism aligns them, simply because the local structure of the galactic magnetic field, which is neither uniform nor simple, happens to orient itself in that particular direction, in that particular patch of space. A coincidence of cosmic geometry, vast in scale, entirely unplanned, that created a situation where the most expected signal of a historic crossing was invisible. Voyager 2, crossing the heliopause, on November 5, 2018, at a location roughly 200 astronomical units away from Voyager. One's crossing point measured laterally across the sky did detect a magnetic field. Rotation, approximately 20 degrees. Not a dramatic reversal, not the large rotation the models had originally predicted, but a clear, measurable change that was absent from Voyager 1's data. Two crossings, two different locations, two different field orientations in the interstellar medium just beyond the heliopause. The galactic magnetic field is structured. It varies. It is not a uniform background field pointing the same direction everywhere. It has its own complex geometry, shaped by stellar winds, supernova remnants, the spiral arm structure of the Milky Way, and currents of plasma that have been flowing through the interstellar medium for millions of years. Two data points, separated by 200 astronomical units, showing slightly different field directions. This is the beginning of a three-dimensional map of the galactic magnetic field in our immediate cosmic neighborhood. Only the very beginning. 2 points define a line, not a volume. The actual structure of the field between and around those measurement points above and below the plane of the solar system, toward and away from the galactic center, all of that remains unmeasured. We have two thumbtacks on an enormous blank canvas. The painting they are part of is still invisible. This matters enormously because of cosmic rays. Galactic cosmic rays are charged particles, and charged particles in a magnetic field do not travel in straight lines. They spiral around field lines following the magnetic geometry, rather than moving directly from source to destination. The direction a cosmic ray appears to come from as seen from Earth, or from Voyager's instruments, depends not just on where it originated, but on every magnetic field it has spiraled around during its journey across the galaxy. The field structure through which cosmic rays travel is essentially a switching yard, routing particles along paths that may be twisted far from the direct route between source and detector. Voyager's measurements of cosmic ray directionality confirmed this in a way the models had not predicted. Scientists expected roughly equal cosmic ray intensity from all directions, a nearly isotropic background of particles arriving uniformly from every angle. The product of so many distant sources that directionality would wash out into uniformity. Instead, both spacecraft detected clear anisotropy. More particles arriving from some directions than others, with the asymmetry persistent and structured rather than random. The cosmic rays are being channeled, Something about the local magnetic geometry is routing more particles from certain directions and fewer from others. The most striking result involves the galactic center. The center of the Milky Way contains the highest density of stars in the galaxy. More supernovae, more pulsar winds, more high-energy events per unit volume than anywhere else in our galactic neighborhood. Naively, one would expect the galactic center to be the brightest source of cosmic rays, the direction from which the most high-energy particles arrive. Voyager's data showed the opposite. Cosmic ray intensity from the direction of the galactic center is lower than from other directions, not higher. The explanation, now broadly accepted, is that the galactic magnetic field is stronger in the inner galaxy, and that stronger field more effectively traps and scatters cosmic rays produced there, preventing them from propagating outward into the outer spiral arms where our solar system resides. The galactic center is producing vast numbers of high-energy particles, but its own magnetic environment is holding most of them in. The practical implications of all this reach directly into Earth's biosphere and climate system. Carbon-14, the radioactive isotope that makes radiocarbon dating possible, the tool that established the chronology of human prehistory and archaeology, is produced when cosmic rays strike nitrogen atoms in Earth's upper atmosphere. The production rate depends on cosmic ray flux. Changes in the local interstellar medium that alter how many cosmic rays reach the inner solar system will alter carbon-14 production rates, introducing systematic errors into dates calculated using standard calibration curves. There is also an active and unresolved scientific debate about whether cosmic rays influence cloud formation in Earth's lower atmosphere, with some research suggesting that ionization from cosmic rays may seed the condensation nuclei around which cloud droplets form. If that mechanism is real, then variations in the interstellar medium over geological timescales could influence Earth's climate through a pathway entirely separate from the solar luminosity changes and greenhouse gas concentrations that dominate current climate discussions. If cosmic rays can influence cloud formation and alter Earth's climate does, knowing that make you think differently about all the factors shaping the world we live in. 7 shocks have now revealed themselves, but a larger question remains, the one Voyager carries with it into the permanent darkness ahead, the one its instruments can no longer answer, the one that belongs not to science, but to something older and stranger in the human character. The power systems that keep Voyager 1 and Voyager 2 alive have no moving parts, no chemical fuel tanks, no solar panels, no batteries that charge and discharge. They are radioisotope thermoelectric generators, 3 of them per spacecraft, each containing a mass of plutonium, 238, sealed inside a protective casing of heat-resistant alloy. Plutonium 238 decays naturally and continuously, releasing energy as heat. Thermocouples devices that convert a temperature difference directly into electrical voltage, with no turbines, no pistons, no mechanical components of any kind, wrap around the outside of each generator and convert that heat into the electricity that powers everything aboard the spacecraft. The elegance of this system is precisely its simplicity. There is nothing to maintain, nothing to refuel, nothing to restart after a failure. The plutonium decays whether anyone is watching or not, whether commands are being received or not, whether the spacecraft is 1 million kilometers from Earth or 22 billion. The decay is a physical law, not a mechanism, and physical laws do not break down. At launch in 1977, each spacecraft generated approximately 470 watts of electrical power, enough to run a few household light bulbs. Enough carefully managed to operate a suite of scientific instruments, maintain the attitude control system, power the radio transmitter, and keep critical components from freezing in the thermal environment of deep space. By 2026, roughly 49 years after launch, Voyager 1 has approximately 249 watts remaining. The decay of plutonium, 238, follows an inexorable curve, roughly 4 watts of output lost per year, every year, without exception, without any possibility of slowing the rate or supplementing the source. 249 watts to operate everything, and everything at this stage requires approximately 245 watts to keep running. The margin between operational and dead is 4 watts. 4 watts is less than the power consumed by a single small LED strip light. On that margin, engineers are maintaining scientific operations of a spacecraft traveling through interstellar space at 61,000 kilometers per hour, communicating with it across a distance that light itself takes more than 22 hours to cross. The management of that 4-watt margin has become one of the most careful engineering exercises in the history of spaceflight. Every few months, the team evaluates the power budget and identifies the next component to be shut down. Heaters that maintain instrument temperatures above operational minimums are switched off first, accepting the risk that the instrument will get too cold to function. Less critical subsystems are put into standby modes that consume fractionally less power. Backup systems that have not been used in decades are activated to replace primary systems that are being powered down. The cameras were shut off in 1990, a decision that felt like a loss at the time, and still does, but freed power that has kept scientific instruments running for 35 additional years. In 2020, engineers faced a decision about Voyager 2's cosmic ray subsystem heater. Switching it off would drop the instrument's temperature to -59 degrees Celsius, 20 degrees below the minimum operating temperature specified in its design documentation. By every reasonable engineering standard, the instrument should have failed. The team accepted the risk because the alternative was consuming power they could no longer afford. The instrument did not fail. Operating at 20 degrees below its designed thermal limit on a spacecraft, launched 43 years earlier, it continued returning cosmic ray data as reliably as it had at any point in the mission. The engineers who built it in the early 1970s had apparently built in margins they never needed to advertise. Communication with both spacecraft flows through NASA's Deep Space Network, 3 complexes of massive radio antenna dishes positioned at roughly equal spacing around Earth's circumference in California, in Spain, and in Australia, so that at least one facility always has a line of sight to the spacecraft, regardless of Earth's rotation. The primary dishes are 70 meters in diameter. Each one is a precisely shaped parabolic reflector engineered to gather the faintest possible radio signals from the greatest possible distances. The transmitter on each Voyager spacecraft produces 23 watts of radio power, less than a standard LED light bulb. That 23-watt signal travels outward from Voyager 1 at the speed of light, spreading and diluting as it crosses the distance 22 billion kilometers as of 2026. By the time it reaches the 70-meter dishes of the Deep Space Network, the signal power has fallen to approximately 1/10-quintillionth of a watt. That is a decimal point followed by 18 zeros before the first significant digit. It is one of the faintest signals that human technology routinely detects and decodes, and it arrives carrying actual scientific data measurements of magnetic fields, particle fluxes, plasma waves from the interstellar medium beyond the edge of the solar system. A round-trip communication exchange with Voyager, one takes 44 hours. Send a command, wait 22 hours. Receive confirmation that the command arrived and was executed. The engineers managing the spacecraft have to plan every interaction days in advance, anticipate every possible response, and write contingency instructions for failure modes before the original command has even arrived. In 2002, NASA uploaded new software to Voyager, one to work around a failing memory module debugging and patching code written 25 years earlier, running on hardware 22 billion kilometers away at a communication speed, where a single exchange took nearly 2 days. They succeeded. Between 2025 and 2027, the last science instruments are expected to be shut down permanently. The power will no longer support them. Voyager 1 will become a metal object, traveling through interstellar space at 61,000 kilometers per hour, carrying instruments that have gone cold and silent, an antenna pointed back toward a sun it can no longer see, and a found, a transmitter that will fall quiet for the last time sometime, around 2030. After that, the only thing still functioning will be inertia. What strikes you as more extraordinary, that technology from 1970 is still working after 50 years in space, or that we can still communicate with something 22 billion kilometers away on a signal weaker than a never. Night like Voyager is dying, but its journey does not end when the signal goes dark, because what it carries requires no electricity to survive, no transmitter to exist, no power budget to endure the centuries ahead. And the story of what it carries into the permanent dark is stranger, more deliberate, and more profoundly human than any of the scientific discoveries this mission has ever made. In the spring of 1977, A small committee of scientists, artists, musicians, and linguists gathered in a room and attempted to answer one of the most impossible questions anyone has ever seriously tried to answer. Not a scientific question, not a technical one, a philosophical one, pressing and urgent, and with no correct solution. The question was this: if you had to explain humanity to a civilization that knows nothing about us, a civilization that may not share our biology, our language, our mathematics, our sense of beauty, or our concept of time, what would you say? What would you choose? What out of everything humanity has ever made or felt or thought or sung is worth sending to the stars? They had a few months to decide. And whatever they chose would be attached to 2 spacecraft, leaving the solar system never to return, carrying their selection into the interstellar dark for billions of years. The idea itself was Carl Sagan's, though he developed it with a team that included astronomer Frank Drake, artist and writer Linda Saltzman, Sagan writer Anne Droyan, and a broader group of contributors who brought expertise in fields from linguistics to musicology. Sagan had already helped design the Pioneer plaque, a simple gold anodized aluminum plate attached to the Pioneer 10 and 11 spacecraft, carrying diagrams of a man, a woman, the solar system, and a pulsar map intended to locate Earth. In space, the Voyager record was a far more ambitious undertaking. Not a plaque, a record, a 12-inch gold-plated copper disc containing sounds and images from Earth, encoded in a format that could in principle survive intact for the age of the universe. The physical design of the record reflects a specific and deliberate choice: durability over sophistication. Gold does not corrode. In the vacuum of space, with no oxygen, no water, no chemical reactions eating at the surface, a gold-plated disc will remain physically unchanged for timescales that make the entire span of human civilization look like an afternoon. The information is not stored magnetically, which would degrade over centuries, or electronically, which would require functioning hardware to read. It is carved into the surface as physical grooves, the same basic technology as a vinyl record, the same technology that has been used to store and replay sound since the 1800s. If the groove structure survives, the information survives. If the information survives, anyone with sufficient technology and curiosity can, in principle, retrieve it. No power required. No compatible hardware required. Just a stylus, a turntable, and the ability to read the instructions etched on the aluminum cover. Those instructions represent one of the most extraordinary feats of communication design in human history. The cover of each record carries a series of diagrams etched in metal, explaining how to play it, the rotation speed expressed in binary notation, using the hyperfine transition frequency of hydrogen as a universal time reference, the positioning of the stylus, the method for decoding the audio, waveforms into visual images. Frank Drake designed a pulsar map showing the sun's location relative to 14 pulsars rotating neutron stars that emit radio pulses at frequencies as unique as fingerprints, their precise periods functioning as a cosmic timestamp, indicating when the record was made, and as a galactic coordinate system, allowing any sufficiently advanced civilization to locate Earth in three-dimensional space. The map is effectively an address, not a street address, a galactic one. What the record contains required months of argument, negotiation, and compromise to decide. The sounds of Earth were perhaps the most straightforward category, though even there the choices involved constant trade-offs. Ocean surf, rain, thunder, the low grinding roar of a volcanic eruption, an earthquake deep subsonic, the sound of a planet's crust in motion, wind in trees. The extraordinary complex vocalizations of humpback whales which can travel thousands of kilometers through ocean water and whose structure suggests a form of communication science still does not fully understand. Bird calls, cricket song, frogs, a dog barking, a baby crying, that specific universal cross-cultural sound that every human being who has ever lived recognizes instantly as the arrival of new life. Human laughter, both male and female, a heartbeat, the sound of a kiss, footsteps on gravel, tools being used, a hammer striking metal, a saw cutting wood, the patient sound of human hands making things. The ignition and thunder of a Saturn V rocket launched the same family of rocket that sent Voyager itself into space. The music selection was where the debates grew most intense. The committee knew immediately that no single musical tradition could represent humanity's creative range. The question was how to balance breadth of representation against depth of artistic significance. How to choose pieces that were both culturally specific, rooted in the particular traditions that produced them, and capable of communicating something true about human experience to listeners who share none of those cultural roots. Johann Sebastian Bach's Brandenburg Concerto No. 2 opened the selection chosen for the mathematical precision of its structure and the emotional immediacy of its sound. Ludwig van Beethoven's Fifth Symphony, Wolfgang Amadeus Mozart's The Magic Flute, Igor Stravinsky's The Rite of Spring, gamelan music from Java, pygmy music from what is now the Democratic Republic of Congo, Aboriginal songs from Australia, among the oldest continuous musical traditions on the planet, panpipes from Peru, shakuhachi flute from Japan, Indian classical raga, Georgian choral singing, blues, jazz, represented by Louis Armstrong, and rock and roll, specifically Johnny B. Good by Chuck Berry. The Chuck Berry question consumed more committee time than it arguably deserved. Some members were concerned that rock and roll, still a relatively young genre, in 1977, still carrying cultural associations that made some institutions uncomfortable, might not represent humanity at its most dignified. Others argued that dignity was not the point. The point was truth. Rock and roll was part of what humanity actually was in 1977. Excluding it because it seemed too undignified for the cosmos would be a kind of dishonesty. Chuck Berry went on the record. When the astronomer John Lennon, not that John Lennon, a different one, heard the news, he reportedly said it was a very good choice. Carl Sagan, for his part, seemed pleased. The universe, he felt, could handle Chuck Berry. Greetings, in 55 languages, accompany the music from ancient Akkadian dead for 3,000 years, but representing humanity's earliest written civilizations in the river valleys of Mesopotamia, to Mandarin Chinese, spoken by more than 1 billion people, to English, Arabic, Hindi, Spanish, French, Russian, and dozens more. Each greeting is brief, a few sentences, expressing peace, friendship, and the hope of someday joining a wider community of civilizations. The words differ, but the sentiment is the same across all 55 languages. We are here. We mean no harm. We hope to meet you. 116 images encoded as audio waveforms that can be decoded back into visual information using the instructions on the cover complete the record's contents. Mathematical definitions establishing that the creators understand basic logic and physics. Diagrams of the solar system. Images of Earth from space. Landscapes, deserts, forests, oceans. Human anatomy depicted in enough detail that any observer could understand the basic biology of the species that made the record. People of different cultures and ages, eating, working, playing, architecture, technology. A page from Isaac Newton's Principia, establishing that the creators understand the mathematics governing the motion of objects. The traffic jam, which in retrospect may communicate more about 21st century Earth than any other single image. Though it was taken in the context of showing human transportation systems, Carl Sagan understood perfectly well that the odds of either record being found were essentially zero. The spacecraft are too small, space is too vast, and they are not aimed at any particular destination. But that was not the point. The point was the act of creation itself. Deciding what to put on the record forced the committee, and by extension, forced humanity in the form of the humans in that room, to think seriously about what they were, what mattered, what endured, what they would want to preserve if they could preserve only a fraction, what they would say if they knew they would be judged after 1 billion years of silence by whatever civilization eventually put a stylus in the groove and listened. If you could choose 3 things to represent all of humanity and send them into the galaxy forever, what would you choose and why? The golden record is hope made, physical hope cast into metal and launched into the dark. But before Voyager disappeared beyond all return, it turned its camera backward one final time, and what it captured in that last look changed permanently the way humanity understands its own place in the universe. On February 14th, 1990, Voyager 1 was approximately 6 billion kilometers from the Sunday. The planetary mission had been over for a decade. The cameras had been scheduled for permanent shutdown to free the electrical power they consumed for the scientific instruments that still had work to do. But before the cameras went dark forever, Carl Sagan had spent years advocating for one final use of them, a request that NASA had initially resisted as scientifically unproductive, but eventually approved. He wanted Voyager to turn around and take one last photograph of the solar system it was leaving behind. The spacecraft rotated its scan platform. The cameras pointed back toward the inner solar system, toward the Sun and the planets orbiting around it. A sequence of 60 frames was captured, covering most of the solar system in a mosaic. 6 planets were visible in the images: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was lost in the Sun's glare. Mars was too faint, Pluto too small. But 6 worlds, including the one that built the cameras taking the picture, were present in that final family portrait of a solar system, photographed from its own edge. In one of those 60 frames, there is a tiny point of pale blue-white light suspended in a diffuse beam of scattered sunlight. The sunbeam is an artifact created by light diffracting through the camera's optics. The blue point is not an artifact, it is Earth. Its apparent diameter in that image is less than a single pixel. The entire planet, all its oceans and continents and atmosphere, every mountain range and river, delta and city and field, the full physical extent of the only home humanity has ever known, occupies less than 1 pixel in a photograph taken from 6 billion kilometers away. Carl Sagan looked at that image for a long time. What he wrote about it afterward became one of the most widely read pieces of scientific prose in the 20th century. And it deserves to be understood not as poetry, but as a precise, literal description of what the image shows and what that means. Every human being who ever lived was born on that pale blue point. Every act of kindness and cruelty, every invention and every destruction, every empire that rose and fell and rose again, every war fought over land that the image reveals to be invisible. At planetary distances, every love affair, every grief, every moment of wonder, all of it took place on a mote of dust, suspended in a sunbeam. Not metaphorically, literally. The sunbeam is real. The mote is real. The dust, compared to the scale of space, is an accurate description of the physical object in the frame. From outside the heliopause, the perspective sharpens further. At 121 astronomical units, the point of light we call the Sun is still visible, but the solar system surrounding it is entirely invisible to any instrument aboard Voyager. The heliosphere, that vast bubble of solar influence that extends far enough to dwarf the orbits of all the planets many times over the structure, whose crossing required years of travel and revealed 7 fundamental surprises, invisible, a small faint star, nothing more. The 400 billion other stars of the Milky Way are each surrounded by their own equivalent structures, their own bubbles of stellar wind pressing against the same interstellar medium that Voyager is now traveling through. Our entire heliosphere, from the perspective of the galaxy, is one small sphere among hundreds of billions. Voyager 1 is currently traveling toward the constellation Ophiuchus, moving at approximately 61,000 kilometers per hour, relative to the Sunday. In approximately 40,000 years, it will make its closest approach to a star, Gliese 445, a dim red dwarf in the constellation Camelopardalis. At that closest approach, Voyager will be approximately 1.6 light-years from that star. 1.6 light-years is roughly 15 trillion kilometers. Closest approach in interstellar terms means passing in the same general neighborhood without any gravitational interaction, without entering any planetary system that may or may not orbit that star, without any possibility of detection by any civilization that may or may not exist there. Voyager will drift past in the void and continue traveling, its trajectory bent by an imperceptible amount by the gravity of a star it will never come close to in any meaningful sense. The nearest star to our Sun is Proxima Centauri at 4.24 light-years, approximately 268,000 astronomical units. At Voyager, one's current speed reaching Proxima Centauri would take approximately 73,000 years. Voyager is not heading toward Proxima Centauri. That 73,000-year figure applies to a hypothetical direct route that the spacecraft is not traveling. The stars Voyager will actually approach in 40,000 years will be encountered at distances still measured in light years, not close enough to orbit, not close enough to communicate with. Not close enough for anything except to note in some abstract calculation that the closest approach distance is smaller than the average separation between stars in this part of the galaxy. The Milky Way contains approximately 400 billion stars. Each one is separated from its neighbours by distances that make the entire heliosphere, that bubble that took Voyager 35 years to cross, look like a dust grain beside a stadium. The space between stars is not empty, as Voyager's measurements have confirmed, but it is overwhelmingly, incomprehensibly, almost insultingly vast. Voyager has crossed our bubble. It is now in the ocean between bubbles. The nearest other bubble, Proxima Centauri's own astrosphere, is 73,000 years away at Voyager's speed. And beyond Proxima Centauri, 400 billion more stars, each with their own bubble, scattered across a galaxy, 100,000 light-years in diameter. The pale blue dot image is not fundamentally a photograph of Earth. It is a photograph of scale. It is a visual demonstration taken with the most literal possible instrument in the most literal possible way of the relationship between a human civilization and the cosmos in which that civilization exists. Every war in history was fought over a fraction of a pixel. Every border ever drawn, every territory ever contested, every resource ever extracted, all of it exists within an object that vanishes at 6 billion kilometers. The image does not argue that human concerns are unimportant. It simply shows, without commentary or interpretation, how large the universe is relative to the stage on which all of human history has played out. And Voyager is the only object ever made by human hands that has stood on the outside of the stage and looked in. The only manufactured object to have crossed the heliopause and turned back toward the light. It saw what we looked like from out there. It showed us. And the image it returned, that pale blue point, barely visible in a sunbeam, is perhaps the most important thing any spacecraft has ever done. Not because of what it measured, but because of what it made impossible to ignore. Knowing that Earth is a point smaller than a pixel in a photograph taken from within our own solar system, does that change how you think about the things that feel largest in your daily life? Voyager showed us how small we are, but it also showed us how far we have reached, and everything it discovered along the way will shape every mission, every model, and every question we ask about the universe for generations to come. The total cost of the Voyager program, from the earliest design work in the late 1960s through the Neptune encounter in 1989, and continuing through the interstellar mission operations that have run ever since, amounts to approximately $865 million across 5 decades of active operation. Spread across 50 years, that figure works out to roughly $17 million per year. A single major Hollywood production, one summer blockbuster, one franchise installment with its visual effects, budget, and global marketing campaign costs more than that in a single year. For the price of one film that will be largely forgotten within a decade, humanity has been running the most distant scientific mission in history for half a century, rewriting the textbooks on planetary science, heliospheric physics, and interstellar space, and keeping 2 spacecraft operational across, a distance that light itself requires more than 22 hours to cross. The scientific return on that investment is not easily summarized because it is not contained in any single discovery or any single data set. It is woven into the foundation of how we currently understand the outer solar system and everything beyond it. Every textbook chapter on Jupiter's moons references Voyager imagery. Every model of Saturn's ring dynamics incorporates Voyager measurements. Every mission proposal targeting Europa's subsurface ocean, and there have been many, and one is currently in development, traces its scientific justification back to the cracked ice surface that Voyager 1 photographed in 1979, and the implications that photograph raised. Every simulation of the heliosphere runs against the boundary conditions that Voyager established through direct measurement. Every discussion of interstellar space begins with the numbers Voyager 1 and Voyager 2 returned after crossing the heliopause. The data exists in NASA's archives, freely available, still being analyzed, still yielding insights that the original mission designers never anticipated asking for. The next step, when it eventually comes, will build directly on what Voyager found, and what Voyager found suggests that the next step needs to be substantially more ambitious. NASA and a consortium of scientific institutions have been developing a concept called the Interstellar probe, a mission designed from the ground up for the specific purpose of exploring the heliosphere and the near interstellar medium in far greater detail than two spacecraft launched in 1977 could ever achieve. The target is 500 to 1,000 astronomical units within 50 years of launch. That requires a spacecraft traveling at roughly twice Voyager's speed, approximately 120,000 to 240,000 kilometers per hour, rather than 61,000. Achieving that velocity requires either a dramatically more powerful launch system than anything currently operational, a close solar flyby using the sun's gravity combined with a high-thrust propulsion burn at the point of two, closest approach, or some combination of advanced technologies not yet demonstrated at mission scale. The mission concept exists, the science case is compelling, the funding and the launch date do not yet exist. If everything proceeds favorably, the earliest plausible launch falls sometime in the 1930s. The spacecraft would not reach 500 astronomical units until the 1980s. The scientists currently designing the mission will very likely not live to see its primary data return. This is the temporal reality of interstellar exploration, and it is worth sitting with rather than rushing past. The Voyager spacecraft were launched when many of the engineers currently maintaining contact with them had not yet been born. The last scientists who worked on the original mission instrument designs are now in their 80s or older. The people who will receive Voyager's final transmission sometime around 2030 are in elementary school today or younger. And the Interstellar probe, if it launches on schedule, will return its most important data to scientists who are currently infants. Exploration at these scales is not a career. It is a relay race across generations where each runner carries a baton they will pass before they see the finish line. But the legacy question that Voyager raises is not only about the next dedicated interstellar mission. It is about the broader challenge of what comes after the eventual, distant, genuinely difficult problem of sending something not just beyond the heliopause, but across the gulf between stars. Voyager's measurements of the interstellar medium have made that challenge more concrete, and in doing so have made it more daunting. The interstellar medium is not empty. It is not hostile in any dramatic sense at Voyager's speeds. But at the velocities required for any kind of practical interstellar travel, 10% of the speed of light is often cited as a minimum for reaching Proxima Centauri within a human lifetime. And that figure represents roughly 67 million kilometers per hour, approximately 1,700 times Voyager's current speed. The interstellar medium becomes a serious engineering problem. At 10% of light speed, every hydrogen atom in the spacecraft's path is effectively a high-energy projectile hitting the hull from the spacecraft's perspective. The interstellar medium contains approximately 0.08 atoms per cubic centimeter, mostly hydrogen, the simplest and lightest atom in the universe. At 1,700 times Voyager's speed, the kinetic energy of each collision is proportional to velocity squared, meaning it is not 1,700 times greater than a Voyager speed collision, but approximately 3 million times greater. A spacecraft with a cross-sectional area of 1 square meter, traveling at 10% of light speed through the local interstellar medium, would encounter roughly 100 trillion hydrogen atoms per second. Each collision individually delivers a negligible amount of energy. Collectively, they deposit several thousand watts of power continuously into the leading surface of the spacecraft, appearing as heat as radiation damage, as cumulative erosion of hull materials at the atomic scale. Over years of travel, this adds up. The materials, science, and shielding engineering required to survive an interstellar journey at meaningful fractions of light speed represent challenges that current technology cannot meet, and current research has only begun to approach. Voyager's cosmic ray measurements add another layer to this picture. Interstellar space has a cosmic ray flux approximately 10 to 20% higher than the flux inside the heliosphere. That difference matters relatively little for an uncrewed spacecraft with radiation-hardened electronics and no biological payload. It matters enormously for any mission carrying human beings or biological samples. The shielding mass required to protect a human crew against sustained cosmic ray exposure in interstellar space would with current materials be prohibitive, likely exceeding the total mass of any spacecraft it could feasibly be attached to. New materials, new shielding concepts, new approaches to radiation biology. All of these are necessary preconditions for human interstellar travel that remain unsolved. There is also the Oort cloud to consider. The Oort cloud is a hypothetical shell of icy bodies believed to surround the solar system at distances ranging from roughly 2,000 to as far as 100,000 astronomical units from the Sunday. It has never been directly observed. No telescope has resolved individual Oort cloud objects, and its existence is inferred from the orbital dynamics of long-period comets that occasionally fall inward toward the Sun from those extreme distances. Voyager 1 will not reach the estimated inner edge of the Oort cloud for approximately 300 years. It will not exit the outer edge for approximately 30,000 years. At that point, in a strictly gravitational sense, the spacecraft will finally be beyond the Sun's sphere of influence, in the space where the Sun's gravity is too weak to dominate the motion of any object passing through. Everything before that, by this definition, is still within the solar system, regardless of whether the solar wind reaches there or not. The solar system is vastly larger than the heliosphere. The heliosphere is merely the bubble of the solar wind. The gravitational domain of the Sun extends perhaps halfway to the nearest star. All of these challenges, the propulsion requirements, the shielding problem, the communication delays, the timescales point toward the same conclusion. Voyager has given us the first direct measurements of the environment any interstellar mission must traverse. And the picture it has drawn is not discouraging in the sense of being impossible, but sobering in the sense of being honest. Interstellar travel is not a near-term engineering problem. It is a long-term civilizational project, requiring sustained investment across generations and scientific advances that have not yet been conceived. What Voyager demonstrated most permanently is something simpler and more fundamental than any of its individual discoveries. A species that has existed for approximately 300,000 years, a geological eye blink, a fraction of the age of the solar system, designed, built, launched, and operated 2 spacecraft that are now traveling through interstellar space. That species used slide rules and early computers and analog electronics and nuclear decay to do it. The spacecraft were built to last 5 years. They have lasted 50. They crossed a boundary no object had ever crossed. They measured things no instrument had ever measured, and they did it by being well-engineered, carefully operated, and relentlessly maintained by successive generations of scientists and engineers who inherited a mission they did not start and will not live to see end. Around 2030, the last transmitter will fall silent. The power will finally be gone, but the spacecraft will not stop. There is no friction in interstellar space, no drag, no mechanism by which a moving object can be slowed. Voyager 1 and Voyager 2 will continue traveling at 61,000 kilometers per hour through the interstellar medium. Indefinitely, not for years, not for centuries, but for timescales that dwarf anything human civilization has, experienced or recorded. The Sun will exhaust its hydrogen fuel in approximately 5 billion years and expand into a red giant, probably engulfing Earth in the process. Long before that, in 40,000 years, Voyager 1 will drift past Gliese 445 at a distance of 1.6 light-years, the closest it will ever come to another star. By the time that happens, modern human civilization will have been gone or transformed beyond recognition for longer than it has currently existed. Whatever humanity is in 40,000 years, if it exists at all, if it still has the concept of a spacecraft, if it still knows what the word Voyager means, it will be something we cannot imagine from here. The golden records will still be attached, still intact, still carrying Bach and Chuck Berry and humpback whale song and a baby's first cry and greetings in 55 languages into the galaxy. Not because anyone expects them to be found, because the act of creating them, of deciding what to put on them, of answering the question of what humanity is and what it is worth, knowing that act was worth doing regardless of whether anyone ever listens. This is the message that the Voyager program ultimately sends not to any extraterrestrial civilization, but to us, to the species that built the spacecraft and watched them go. Science does not always give us the answers we expect. Models built by brilliant people using correct physics can still be wrong in the specific because the universe is more complex than any model. Every time we send an instrument to measure something we thought we understood reality surprises us. not because we are bad scientists, because the universe is genuinely, persistently, inexhaustibly richer than our best descriptions of it. 2 metal boxes launched with slide rule calculations, traveling forever through the dark between stars, carrying music and mathematics, and a map home. This is what a species of 300,000 years looks like when it decides to reach beyond everything it knows. 50 years from now, what do you think humanity will send beyond the solar system next, and what will it carry? 2 small metal boxes built by people who used rulers to calculate trajectories are falling forever into the galactic dark, carrying the laughter, the music, the heartbeat of a species still, learning to look up at the sky. And though no one is waiting for them, they go anyway, because that is the deepest instinct of conscious life, to reach beyond the known, even when there is no certainty that anyone is out there to see it.